Hello? Okay. Well, hello again, everyone. I'm back now with my Hawkeye 360 hat on. And what I'm going to talk about here is an application that we put together over the past 2 years. And it's basically a high-rate heterogeneous FPGA processor transport. And I'll walk through that. But before I do, I want to provide a little bit of background to what Hawkeye 360 is doing and why this is relevant to us. So some of you may be familiar with the concept of Hawkeye 360. We're a small sat company who is launching a constellation of small satellites. We are flying 3 in a cluster with co-visibility of the ground. They receive data from receive RF data. It's basically flying software-defined radio from space. They receive data from emitters on the ground, and we make TDOA, FQA measurements of the received signals on each platform, and then we turn those into geolocation, so we find the location of the emitter. And the goal is to become a commercial data source for RF geolocation and analytics. And the technical problems we solve are pretty similar to everything that we're talking about here this week. One of the big ones is how do we capture a lot of data with a small amount of power. And that's really important for us because the power that's available to our software-defined radio is about 5 watts in what we launched this year. So small, it needs to consume low amounts of power, and it has to be performant. It's got to be able to actually record RF data.
Sorry.
Right. So this is just a quick walkthrough of what I'm going to talk about today. We're going to specifically focus on the E310 transport and DMA because technically what we basically designed is a platform that uses UHD, RFNoC, and Gnuradio. And it's modeled to look like E310, and if E310 doesn't receive 40, 50 megahertz of data, then we need that to work well for us. So I hope this will be educational. I was very excited to see the previous talk about the visionary ideas of heterogeneous computing defined in OpenCL, but in practice, we've got to make something that works, and we've got to deploy it today. So we have to have something that works. So what I'm going to do here is talk about the first principles of what the problem is, how we transfer data between an FPGA and a processor. We're going to talk about the solution, which is the direct memory access, and we're going to talk about what we did to be able to make this work for us in space. All right, so we've got a low-power device. We can't do everything in the processor. Like I said, we have 5 watts of data, or 5 watts of power available, and that's about enough for a Zynq system on chip, plus a 9361. We don't have a big processor that we can use. We can't throw 50 to 100 watts at the problem and 8 cores and be happy with that. We have to be more efficient about the computing power that we have, and that means that we have to transfer data between the processor and some other computing architecture. In this case, an FPGA, but in many cases, this data transfer becomes a bottleneck. So there's just a couple examples here. The GPUs, you've got the AWS F1 instances, which have a big FPGA situated next to a processor, a PCIe, and even a pretty cool example of a M.2 interface FPGA. And there you go, there's the takeaway point. And if you want to do it for software-defined radio with low power, low swap, you've got some good options. You've got the Ettus family of E310s, you've got the EPIC solution, so the Z2's got a Zynq on it. There's Line that has an Altera version, and since we're deploying a silent Zynq, that's what we're going to focus on. That's also similar to E310 and the For an example, let's just characterize what E310 gets as far as just trying to take data from straight off the 9361 and save it to disk. And if you just transfer the data from the FPGA to the processor and with like a benchmark, you use a benchmark rate application, or you put it into Gnuradio with a null sync. So it shouldn't be doing any file I/O on the storage side. I was able to get about 10 megahertz receive only without overflows, which definitely limits the amount of data you could put into the processor. But if you are trying to write to file, the best I could find was about 1 megahertz on a good day. And this is where I was testing for 30 seconds at a time and 16 shorts. So kind of the takeaway here is that, you know, in an ideal world like the previous presentation, we have something that does this for us, but oftentimes we'll find that the thing we're doing doesn't quite hit those limits. So let's talk about why and what we can do to fix that. And the solution, which is what all these devices try to do, is a direct memory access DMA transfer. And the concept of this is that the processor can't really service the entire mem copy itself. You know, the ARM has some amount of processor rate, 600 megahertz or so, depending on what ARM you have, and you just can't transfer that amount of data and do other relevant stuff. So the idea is that you have some hardware feature that's able to perform the copy asynchronously and without processor involvement. What are the hardware architectures that do DMAs? So the first one to talk about is what's called the scattered gather DMA. And the idea here is that the hardware that you're using is able to look at memory pointers. You can configure all this ahead of time, and then the hardware that's doing the transfer chains together multiple DMA requests. So it'll transfer data, and then it'll read the addresses for the next transfer, and then it'll go ahead and do that. So the processor can set up a bunch of transfers at once, and the FPGA or the hardware, whatever it may be, is able to go ahead and execute that. This has the least amount of so processing system interaction. The other version you could do is something that's called a direct register mode. So this is kind of like I often call it the non-scatter gather. So if you put the processor in the loop for every buffer transfer, then the processor will write the source destination, write the source address, write the destination address. Then the hardware goes and does that. It sends an interrupt that says I'm done, and the processor can go handle that and set up the next one. So it requires a little bit more processor interaction, but it's a little bit easier to set up and implement. Specifically on the Zynq, the question becomes, what is the theoretical limit, and how do you do it? So how do you do it? The FPGA fabric, you allocate a DMA controller IP core, and this is similar to the Altera. And the IP core is able to access the memory transfer crossbars and the memory interconnects on the Zynq hardware, and you can write data in and data out. And if you look at the Zynq manual, you see that for the high-performance AXI bus, you could get up to 1,200 megabytes per second, and that's pretty high. You're never actually going to get there because there's overhead associated with each transfer. You have to packetize the packets that go onto this memory interconnect and the high-performance controller. So you won't quite get there. And on top of that, you also need to share the controllers with other things. So if you have a DMA that's accessing that and then something else, then you actually have to split the bandwidth. So there's a lot of reasons why you won't get the full bandwidth, but ideally you could get pretty close. And 10 megasamples per second with interleaved IQ, so 4 bytes per sample, and it's only 40 megabytes per second, and it's not quite near the theoretical bandwidth that we're looking to be able to support. Also on the Zynq, and for other FPGA-based concepts, you'll see possible channels where you go, the terminology is a memory mapped to stream, And so that's a DMA that reads from the memory, so memory mapped, and then it becomes a stream. So this is like an AXI stream interface that you see on the FPGA, and you can read out the samples. And then the vice versa is stream to memory mapped. It's like you're trying to read stuff off of 9261. This is the thing I'm most interested in, which is taking samples from a streaming interface and putting them into memory. And then when the processor is interacting with that, you use AXI Core Lite interface, which basically is a lower throughput interface, but it lets you set the registers in a pretty easy way. When you're doing the software, how do you write the software? On the left is a polling driver, which is probably an easier way to do it. You can run the processor in a tight loop and respond quickly to DMA. So if you look at the tutorials of how to actually do a DMA or interact with IP core, you'll see something like this. It's written in user space. You twiddle some registers, and you do a copy that goes from one place to another. Really, actually pretty easy. You can get that up and running in a matter of hours or so, or tens of minutes probably. On the other hand, the other software option is using an interrupt driver. And ultimately, DMA software is going to use a kernel driver because you have to be able to service the interrupt request, which is not something you can do in user space. It's more difficult to do because you have to do a kernel module. But we're here for software-defined radio, and it kind of fits in the 5 overlapping Venn diagrams that Robin showed earlier. So, I got to do it. Okay, what did we specifically do for our spacecraft? Sticking with the UHD and RFNoC architecture, we did some major surgery. This is a quick overview. So we made a new RFNoC block that essentially pulls data off of the AXI wrapper and the NoC shell and feeds it into Xilinx IP core that does the DMA. So it goes stream to memory mapped. Next, we wrote a kernel driver in order to service these interrupts. After that, we have a UHD block controller that is able to twiddle the register reads and writes using RFNoC's helpful infrastructure. And then in Gnuradio world, we override the general work function, like as per everything else, and feed the samples into Gnuradio and just use file sync operation. The trick here is that the DMA that we put together uses larger packet sizes, so I'll talk about that a little bit more later. This is just illustrating the architecture I was discussing. So we have in the RFNoC block is the black dotted line. We've got the NoC shell, AXI wrapper, and then we add some extra I/O. It goes out and it goes to the AXI DMA IP core. When you're using the Xilinx IP, you've got an option for a data mover, which provides the core data transfer functionality, and that one's a little bit difficult to use. You kind of have to implement your own protocol. And then the AXI DMA adds more logic to be able to do the scatter gather or direct register operation modes, kind of more out of the box. Okay, moving up the stack. We've talked about FPGA, now let's talk about the kernel driver. We started off trying to work with the Xilinx AXI DMA Linux driver. There's a long story with that one. I won't go through each individual point, but at the end of the day, for that, we weren't able to get it to work in any reliable way. We even tried adding up streaming patches for this, and it was still unreliable with the lockup. And so now maybe 2019, maybe it's better, but we haven't actually returned to that one. Another option, there's the libiio driver. And that's really tied also, I believe, well, I won't speak for the libiio analog devices people, but I'm also excited to learn more about that. We wanted something a little bit more basic and specific to our specific needs, so I will add this fun comic here. Now there are 15 competing standards. All right, so what did we do? Basically, the simplest kernel driver you can ask for. Service an interrupt request when it's available. We've also pre-allocated the memory. So also, Robin mentioned earlier, in the Pluto has about 128 megabytes, I believe it was, continuous memory allocation. We do something similar here. We use 160 megabytes. We can get 1 second of 40 megahertz data buffered up into RAM. So we pre-allocate these memory buffers, and then we have a kernel driver that swaps out the buffers on demand. This is, it uses interrupts, and it does use direct register mode as the quickest path to success. But the trick here is that we're using really large buffers. We have 160 megabytes of RAM, and then we transfer in 128 kilobytes, which if you're running at a low rate, is going to add a lot of latency, but if you're running at a high rate, you're going to decrease some of the processor load. So this is pretty much the real big trick. Okay, kernel driver, now let's go up the stack a little bit more. Next, you have user space software. So when you're working in user space software in the Linux world, and you want to interact with the kernel driver, you can use a read or an mmap. And the trick here, I mean, you definitely want to use mmap. So you'll map the kernel buffer to user space, and then you free the buffer when it's done. So the buffer fills up from the DMA, the kernel says it's ready, give it to user space can do what it wants, and then when it's done with the buffer, then it says that it's done. So how exactly does this look? UHD holds our block controller that interacts in user space with the custom kernel driver. And then on top of that, we have a Gnuradio hook that grabs the block controller and is able to pull stuff into Gnuradio. And that leads me directly into this slide, one additional level higher, which is how we do Gnuradio with this. And I mean, it's pretty straightforward. The Gnuradio scheduler calls the work function, asks for some amount of samples. We fill the output buffer with samples and save the rest. Next time it's called, it fills in more data. And the goal here is just we just want to record as much as we can straight into Gnuradio. For our particular application, we didn't care too much about latency, so it makes these large buffers feasible. We only did one channel, so we could do more. Very low flexibility and large latency. And the question that I'm interested to learn, one of the questions I'm interested to learn this week, I wrote some talk about it last year, but are there better ways to transfer data to and from Gnuradio besides creating a new block that has a general work function that interacts with your heterogeneous software? That's what we've done here. That's what we've seen in most other use cases, but I think it's an interesting inquiry when we're talking about where Gnuradio moves going forward. All right, so that was pretty much the full stack. I want to add another twist here. So recently, in the last couple of months, we found that we have a lot of small packets that we need to be able to support. And so our use case turned from one where we had continuous streaming data, and we wanted to write that into Gnuradio, to one where we had lots of small packets, probably 256 bytes or so, and each of those was self-contained. It has like a start time and some number of samples, and they're not really linked to each other. So based on the old, the streaming architecture, we cut it off if we saw kind of like an inverse sort of scenario, and where we needed to interpret a timestamp differently. But what we did here was we reworked some of the FPGA to just coalesce these packets, and so you can see the diagram of the RFNoC block, which used to have a NoC shell and an AXI wrapper that pulls the information off of that. We actually are just kind of X'd out the AXI wrapper, so it comes straight from the shell, and we take the entire packet and we push it into the AUX the AXI DMA IP core, and then that goes into Gnuradio. And then on the Gnuradio side, we can look at the packets, use the UHD cheddar parsing, pull out the packet information, and then we could either convert them to PPUs or just dump the data straight to disk. And that lets us get an order of magnitude larger, more small packets than we had before. And we could even add some extra flexibility here. So if we wanted to put multiple channels into this block and pull that into the software, we could do that and support up to full rate transfers. Okay. What are the results here? So if there's no PS load, max continuous receive rate without overflows, it can go higher. We test to 40 because it's convenient, a nice round number. Now, if you're ready to file, though, there's a bit of a hitch when you're ready to file, and that is that actually doing the file I/O takes non-zero amount of browser time. And if your kernel driver is trying to service the DMA interrupts, and it's also trying to service the I/O to write to the SD card, then they kind of fight with each other, and we top out around 4 megahertz continuous, which is partly driven by the I/O fight, and it's also actually partly driven by the max data rate that you can write actually to the SD card. So there's some point on like the E310, for example, where the SD card only supports maybe 20 to 30 megabytes per second, and you're not going to be able to sustain any higher than that. So the other thing we did is turn this into a bursted receive rate, where we collect a contiguous chunk of data, put that into the RAM, and then we write data from the RAM onto the hard drive and burn off that data. And that can also achieve the full rate. We haven't done it for 2 channels, but we expect that we could probably do that too if we need to. All right, what are the trade-offs that we make here, kind of from the first principles basis? So, RFNoC, you've got small DMA buffers, which gives you lower latency. That's a good thing. It increases your flexibility. It allows you to route packets to different parts of your crossbar if you're trying to use multiple blocks on the crossbar. If you're trying to actually use the FPGA as part of your software-defined flow graph. But on the other hand, having smaller packets increases the required processor load, and at least for the ARM, you can't support as much data as you theoretically could if you have larger buffers. For our application, we want to be able to record the full rate, and so we implemented larger DMA buffers. We don't use the scatter gather. We just use the direct register mode for simplicity, and we work up to the full bandwidth. So the key point here is that I think this is a good takeaway point actually, which is that I hesitate to say a better or worse result, because they both have their place. So let's consider the actual implementation when we do it versus the goals of your application when we're creating this layer. All right, so at the end of this, I hope that I've provided enough of a crash course here for you to feel equipped to address these issues, or at least understand what some of these things are doing behind the scenes, if they are or are not living up to the expectations that you have. And I also want to emphasize that the full rate heterogeneous transfers into and out of Gnuradio are possible on embedded Zynqs. And I hope this can inspire more people to look into that.